Okay. Well, I will start by thanking the organizer for letting me the opportunity to speak today and organizing this very nice conference. And now I will start my talk. So I will speak about some theory we have been developed with Jorge Zanelli and Mauricio Valenzuela and also Pedro Alvarez. And this is a continuation of works already begun quite some time ago and involving a lot of people. So among others, there is also Pablo Pais, which is here in this conference this week. And so I will recall the construction. So the standard gauge theory are built using a field which is called a connection, and which is a Lie algebra valued one form, if you describe it mathematically. And this standard gauge theory, you have Young-Mills, you have Chen-Simons. Okay, and then if you add matter, so you add the matter Lagrangian, the matter field will be in the representation of the Lie algebra, in which the connection takes its value. So here, instead of adding this Lagrangian matter, we propose to use a super algebra to have the matter field also in the connection. So we will build a super connection which have as bosonic part the standard bosonic connection, bosonic field, and the odd part will be the matter which will be already in the connection. Okay, so the super algebra we use is SU22 or bar 2, and so it is defined as this set of matrices satisfying this relation here. Here for this super matrices, let me recall just that the bosonic part is a diagonal and the odd part is the off diagonal. So this super algebra has bosonic subalgebra SO for 2, SU2, and U1. So SO for 2 is a conformal algebra. It contains Lorentz algebra, and that's what we are interested in. And SU2 and U1 will be the internal symmetries algebra. So from this super algebra, we form a connection, which is written here. So it is a one form which has value in this super algebra, and we denote each field by indices with respect to their generators. And from this connection, we built its curvature, which would be this standard GA plus 1 alpha A wedged A. And here's the D full at the very end of the slide, which is here. It's a covariant derivative with respect to all bosonic fields, so all these fields here. Okay. And now we want to build an action from this curvature. So we want to use something similar to Young-Mills. So we will build super trace of some F, Hodge F. But if we take just this operator here to be the usual Hodge, we will get something like this. And this is not the standard matter Lagrangian. This will contain some double derivative of the fermion, and it's not what we want. So and if instead we use I gamma 5 instead of Hodge, we get this, and this gives the Harita-Schwinger Lagrangian. So this, okay, the idea of using I gamma 5 here is not new, and what's already introduced by MacDowell and Mansouri. So that's why I call it extended MacDowell-Mansouri. Okay, so now we need to define this operator, and for this we have to impose to it some properties. So the property we will impose is, first, it has to be an automorphism of this space of super algebra 2 forms. It has to preserve the observed symmetry of nature. So it has to preserve Lorentz, so it has to be invariant on a Lorentz transformation and SU2 and U1 transformation. Okay, and we also to be the urge operator when restricted to SU2 times U1 to get the Young-Mills Lagrangian for this field. And also we had the restriction that just 2 squared to -1, so to mimic the urge operator in Lorentz spacetime. Okay, so here I present you all the possibility you can have. So here's for the Young-Mills fields, you have only Hodge operator. And then for the Lorentzian curvature, you could have I gamma 5 or Hodge operator. For the dilatation, you only have Hodge operator, and where you really have choice is on the translation and special conformal transformation, where here you can play with some parameters, and here A, B, and C are just function of two parameters, but are complicated function of two parameters. So you have, so I wrote like this, but in fact you have only like 2 degrees of freedom, so to speak. And I gamma 5 is this matrix, so just to act in the good place. Okay, and for fermions, we will restrict ourselves to this. Okay. In fact, the two possibility you have either this one or this one. Okay. I will already say the main motivation is to use this operator. So here is the choice we made. Just take Hodge operator for Young-Mills and for dilatation. We choose I gamma 5 for all other bonic fields, and I gamma 5 as well for the fermionic part. And we can compute our Lagrangian, and this is the Lagrangian we get. So we can analyze the term yes. So the first line, it contains something which will become the Einstein-Hilbert Lagrangian plus a cosmological constant under further restriction. The second part is the Young-Mills Lagrangian. Then the third part is Harita-Schwinger with gauge covariant derivative here. And then you get some other terms. So you have one which involves the torsion, one which is the topological term, and you also have the appearance of some currents. So for fermion interaction here, where J are some currents. So JB here means that we use gamma AB. JI is we use I sigma I over 2 and G5 gamma 5 over 2. So here's a please notice the covariant derivative here are reduced, and now we are only using this covariant derivative. So particular the H has disappeared. Also, note that the H only appear here, here, and here. And in fact, under further restriction, this term will cancel, so we will just have this term and this term. And so somehow, under one more assumption, this will cancel and H will completely decouple. Okay. So now
5 minutes.
Okay, thank you. Now what we can do is identify P plus and P minus with the field bind, so exactly 1/2 of the field bind, and resolve the equation of motion for the spin connection and obtain the torsion. So this is the usual, we get the usual formula for the torsion, and now this part has become really the Einstein-Hilbert Lagrangian plus some contortion term here. And here's now the covariant derivative is with the spin connections, field bind dependent spin connections. So, okay. So now there's one thing one can do is look at some submodel which come from the subalgebra of big algebra. And the subalgebra is OSP42R. So this is the definition of OSP42C, and OSP42R is just to restrict to real coefficients. Okay, and so here I have the connection for OSP42R. Now I need to introduce a new generator, which is a combination of Q and Q bar. There is only one Young-Mills generator which survive, which will be now a U1 field. And this is the Lagrangian we obtain once we restrict to this OSP42 model. So one thing one can do now with this OSP42 model is compare to some standard supergravity, n equal to supergravity. So one we looked at is the one which is in Ortin's book. And we observe that some terms are the same, and we have some new terms. So, for example, new term this one here, this one here. Okay. But for example, this one is in Ortin. Well, of course, this is in Ortin. This also is in Ortin. Okay. And so now we can ask ourselves if the theory is supersymmetric. So this is the last part. Of course, by its very construction, the theory is not supersymmetric because we break the supersymmetry by taking an operator which is not invariant. So this is what I mean here. We take this Hodge operator which is not invariant under the full superalgebra, but only, as I say, Lorentz and internal symmetry. So it's only invariant under this symmetry. So only the symmetry that's preserved. And as such, supersymmetry is not preserved. But what one can show is under further restriction, we can recover supersymmetry. So one is the restriction is the torsion constraint. So we have to put this P equal field binds and solve the torsion equation. Then we get the torsion constraint. So this is standard in supergravity theory. But we need another constraint, which is a Harita-Schwinger equation, which can be written like this. So this is, if this equation is satisfied by the fermions, then we have supersymmetry. So we have restricted supersymmetry in some sense. And well, this is the end of what I wanted to present to you. So thank you a lot for your attention. And these are some references you can look at. So the first three are similar models, and the last one is a paper of MacDowell-Mansouri. Thank you a lot for your attention.
So thanks to Lucas for this talk. We have time for many questions. So is there any question? Francisco? So Francisco is not here, but he has the hand. Well, meanwhile, please, Joaquim.
Okay. Could you comment about the relation with this, the supersymmetry of different kind? I don't see immediately connection.
Okay, so supersymmetry of different kind, which was published in 2012. Yeah. So if I remember well this article, it was just they just had U1 field. So here we take some SU2 more, so we take a bigger algebra, and also they make the assumption that here this psi was in fact, so here it's a 3/2 spin field, and they took the assumption it is the field bind composed with spin 1/2 field, spin 1/2 field. So here we look at some more general setting where this is a spin 3/2 field, and we also implemented SU2. So this add of the SU2 sector was already done in this paper, and really from what changed from here to what I've presented to you is this change of the spin-off field from spin 1/2 to spin 3/2.
Okay, thank you.